I have already posted several examples of Stokes Theorem in application problems on the math blog, and I encourage you to check those out in detail. But let's talk for a few minutes about where Stokes Theorem comes from and what are some of its features. In particular, Stokes Theorem says that the line integral, basically of the work that you do by going around the boundary of a surface, is equal to the flux, that is the surface integral of the normal component, of the curl. And that can look pretty obscure, but let's talk about some of the implications. First of all, don't forget the right-hand rule. It's important that if you're looking down at this surface from above so that C is oriented counterclockwise, it's basically the right-hand rule, then unit normal vectors for this surface will be pointing upward at you from your point of view. All right? So now let's take this back to its origin in Green's theorem. That's the theorem that looks very similar in that if you had P dx plus Q dy, it's planar. Remember, these are basically the same thing in different notation. If you have a region over here bounded by a closed curve that is oriented counterclockwise, so here's your domain, you can integrate the difference of the partial of Q with respect to X and the partial of P with respect to Y. And that's going to be with respect to area. So that's the statement of Green's theorem. This curve C must be closed. That's what the little circle there means. And we have the little circle here in Stokes' theorem as well, a boundary for the entire surface. And here we have this planar region D. And we do recall, at least I hope we recall, that this was the third component, the Z component of the curl. So you can get that in the following way. You can take the curl and dot it with K, because that's how you get the third component, the Z component. And over here on this side, you can simply write this as F dot dr, which is simply playing with notation. Now, if you take a look at what's going on, right-hand rule, if you put your fingers curling around C, your thumb would point straight up, and that would be the right-hand rule. So, in other words, we took this planar example and we elevated it. The surface went up into space, or down into space, wherever it happens to be in 3D, and this is no longer a constant because n, the unit normal vector, is a unit pointing in whatever direction necessary over the entire surface. All right? So work around the boundary equals the flux of the curl over the surface. Now this has an immediate application that might not occur to you offhand. On the one hand, it's fairly obvious that these theorems give you a choice. I can do the line integral, or I can do the surface integral. I can do this line integral, or I can do this area integral. Whichever one is more convenient. But get a load of this. If S1 and S2 have the same boundary C, then for both of them, Stokes' theorem says that they equal this work integral. So they have to equal each other. The integral over S1 of the curl dotted with n is going to be the integral, double integral over the surface S2 of the curl dotted with whatever n is for this other surface. This is an example of surface independence. If you don't quite appreciate what this means, well, check this out. If, for example, I had some nice surface in space right here, and maybe it's a hemisphere, maybe it's part of a paraboloid, and I call it S1. And C is just this. Looks like it would be a circular, maybe elliptical, but it would have a nice oriented boundary. And unit normals would bristle upward from it. But suppose I use the same boundary C and instead I build something else on it and call it S2. They would still have the same result. Or I could even go all the way up and put a lid on it and make some kind of cylinder and call it S3, and S3 would have the same flux for the curl that S1 and S2 have. I could even blow this up on top and make a kind of chef's hat, as long as it still had the same boundary on the open side. Remember, these are closed except for this open part underneath. Or, here's the best part, you could pancake it all down into a surface, which is just a disk floating in space. I could call it S0, and that might be the best of all. All of these would have the same result if I compute curl.n over the surface. So it would be up to me to pick which one to use. And as I said, I've posted examples that use these properties on the math blog, and you really should check those out.